Oh yeah. Oh yeah, we are.
So I was told at the beginning of the semester by Peter that not only would this be the most incredible presentation in the history of presentations, but that I would personally thank him for the incredible awesomeness that they had done at the end of this presentation. So with that set up, off you go.
Well, Zane, you're always so good at introductions. My name is Peter. I got into robotics because my granddad was a civil engineer and he introduced me into the industry. And I wanted to take that a step further and pursue the future of engineering, which is automation and robotic assemblies.
My name is Jonathan Ingram. I was interested in robotics during my high school career, and my mentor and high school teacher, Rodney Ragsdale, was a huge impetus in my life for that.
Hi, I'm Darbey Maza. When I first started college, I really didn't know what I wanted to do, and I got into engineering by the people I was hanging out with. And when I found out about mechatronics, I just thought it was kind of the coolest, engineering, and I'm glad I'm graduating with this degree.
And I'm Andrew Wentworth. I got into robotics just through some natural exploration and things in high school. But getting into college, I realized that mechatronics and automation as an industry were a great way to leave a positive mark on the world.
All right, so let's move into the presentation. So this is the Senior Mechatronics Capstone Project Aria, or Autonomous Robotics Intelligent Assistant. Again, my name is Peter Jacobs. I'm the Project Manager and Artificial Intelligence Lead.
My name is Jonathan Ingram, Communications Director and Mechanical Lead.
I'm Darbey Maza. I'm Navigation and Hardware Lead.
I'm Andrew Wentworth, Audio Lead and Speech Recognition Officer.
So what is the project that we're trying to solve? Currently right now, there are a lot of virtual home assistants, such as Alexa, Cortana, and Google Assistant. However, a shortcoming of some of these is that they are very impersonal. They're small discs or circles sitting on a surface, and they're also static. So they don't move, they don't interact with you at all.
So when we decided how we wanted to improve, or were wondering how we could improve a personal assistant, we thought about making them mobile. The current market has a few mobile robots that either have wheels or legs, but a big disadvantage of this is they aren't able to navigate a house and go upstairs. So we thought of doing a drone. Aria can easily go upstairs and it can easily turn tight spaces.
So as Peter and Darby have shared, there's a clear need for a mobile personal assistant. We also wanted a personal assistant to be a little bit more personable to each user that is interacting with it. For Aria, we wanted her to be able to fly for up to 10 minutes, recognize 4 unique faces of the users to have a more personal interaction and assistant side, as well as being able to execute 3 preset voice commands, which we have linked to our APIs and a joke script, and perform in 2 autonomous flight modes to navigate the home environment, all while meeting FAA standards for small unmanned aircraft systems.
So a few of the standards we designed from by the FAA were we wanted an aircraft under 55 pounds. We stayed way under this by having Aria at about 1.44 pounds. For maximum ground speed, it's 44.7 meters per second. Aria flies at max 13 meters per second. Although Aria can hypothetically fly up very high, she is programmed to only stay at 5 feet. For pre-flight inspections, we used our software Q ground control, which checks GPS, safety switches, and voltage before we'll arm the drone. And lastly, and most importantly, Aria is not carrying any hazardous materials, like explosives.
Hey, Aria.
Unix is user-friendly. It's just very particular about who its friends are.
The current temperature is 65.4 degrees Fahrenheit. The weather is currently few clouds.
Hey Aria, what's on my calendar?
You have an event Aria presentation day at 12:30 p.m. on April 30th.
So, from that video, it showed up a bunch of different functionalities of the drone, and we have a bunch of hardware stacked all on top of it. One of the largest components is the Jetson Nano, which is a single-board computer developed by NVIDIA. We compared the Jetson Nano with a couple alternatives, such as the Raspberry Pi 4B and the Rock Pi N10. We ended up choosing the Jetson Nano for its sheer computing power, and also all of the ports on it to allow us to connect to different functionalities. We're using the Jetson right now for speech recognition and facial recognition.
We used a Picktalk 4 flight controller to get our drone into the air. The Picktalk 4 was basically a sensor hub that connected all of our ESCs and motors and to make sure everything was working together. We also implemented 2 cameras onto our drone, a Raspberry Pi V2 camera and an RGB depth camera. Our Raspberry Pi V2 camera was in charge of facial recognition on the Jetson, and our RGB depth camera was used for navigation. The depth camera allows us to stay a safe distance from any user.
For our sound management, we implemented a unidirectional microphone to control for rotor noise, and we added a small laptop speaker to Aria to allow for her to get user feedback without adding significant weight to the drone.
We also decided to implement Qi charging to eliminate the need to change Aria's battery between flights, and for communications for the weather APIs and other network necessary systems, we have the integrated Intel Wi-Fi card.
We chose a lot of our components based off compatibility, affordability, and durability. The first component we chose was the Jetson Nano. It has a lot of different functionality, and as Peter said, there are a lot of ports built into it that we needed for our subsystems. Second, we chose the Picktalk 4 flight controller. This was suggested by the AUV team here on campus. And as we looked into it, we saw how compatible it was with a lot of different ground control software, and also how compatible it was with the Jetson. The Picktalk came with a GPS module and a power management board, which also played into the decision. The LiPo batteries, Andrew will talk about a little bit later, those specs. We used BL Heli ESCs, which were probably the least compatible thing on our drone because they all had to be calibrated individually, but they were very affordable and did an amazing job leveling our flights. We used ready-to-sky motors because they were the perfect size, and also Andrew will cover those too. We had to get a receiver and a controller for our flight tests for Aria. We didn't want to spend a lot of money on this area because we wanted to go autonomous. So we went with the Fly Skies, which were compatible with the Picktalk and were also perfect for our project. And then finally, we used a Raspberry Pi V2 camera on the Jetson. We liked the Raspberry Pi because it was perfect for the Jetson. And finally, our frame, the iFlight Fedora SL5. We like that because of its size and durability. Aria has taken more than her fair share of falls, and all of our components have been really well protected with that frame.
We also had to 3D model and print several parts for the drone frame. In the top left, we have a mount for the Picktalk that allows the Picktalk to be mounted on top of the chassis and oriented in the correct direction for flight. There's also a power distribution board mount on top of the Picktalk, just so all the wiring can stay in one concise location. The top right image is a mount that was created for the 2 Pi cams, which were originally going to be Aria's eyes. This mount also allows for the cameras to be pitched up and down, depending on the need. The bottom left is a Jetson Nano case that was pulled off of a model from Thingiverse and modified to mount underneath the drone, as well as housing a Qi charging coil. And the bottom right is a beautiful model made by Andrew for the unidirectional microphone.
So here you can see our preliminary function block diagram. We went through a few designs before getting to our current design. For our first one, we had 2 companion computers, both a Raspberry and a Jetson Nano. This added a lot of unnecessary redundancies and was kind of expensive. So we decided to just use the Jetson Nano on board the drone. This brings us to our second design. And for our second design, we implemented 2 Raspberry cameras, one for facial recognition and one for a navigation software called SLAM. We decided later on SLAM wasn't the best way to navigate, so we changed one of our Raspberry Pis to an RGB depth camera. This brings us to our current function block diagram. A lot of the components are similar. However, you can see one of our cameras was changed to the RGB depth camera, which also got rid of a proximity sensor. Our motors, ESCs, and battery are all connected to the Picktalk power management board. This then connects the Picktalk flight controller, which reads in the signals from the ESCs and corrects the yaw and pitch to perform a level flight. All of our AIs and personal assistant aspects of Aria were connected to the Jetson Nano. We will also reference this function block diagram later on in slides so you can see how subsystems work on it.
This image is the charging circuit that was constructed for Aria's wireless charging. On the left-hand side, you will see the home base, which serves as Aria's home when she is not being navigating around the house. This houses the Qi charging transmission coil, which when Aria is on the home base will connect with the receiving coil, which then powers the LiPo battery through a balance charger, which frees up the primary lead to connect to the power distribution board to power both the Picktalk, the Jetson, and all the ESCs.
Here is a little compilation of our drone build. First, we have the frame build where we put our ESCs, motors, and power management board and got those all soldered together. Next, we attached our 3D printed parts. On the top, you can see that is where the Picktalk flight controller goes, and on the bottom is where our Jetson Nano goes. Next, we configured everything and got it all working as one distinct unit. Then you can see our first flight, which has 2 different types of propellers. We found Aria was a little off balance, so we tried to correct this by using the 3 propellers in the back, or the 3 blade propellers in the back. It didn't do much and actually added a few more problems, so then we changed to all 4 of the same propellers.
Now, in designing Aria, we want to start from the ground up. So this meant that we had to create a drone platform that would be capable of supporting the total weight of Aria in the end. To accomplish this, we came up with a standard range of acceptable weights that we were comfortable saying would make up the total of Aria. From there, we decided upon a motor that would accomplish enough thrust-to-weight ratio within an acceptable range that we would be able to efficiently fly Aria autonomously. This ended up being a total thrust of 1,760 grams for us. To choose a frame, we wanted to choose something that would compactly fit all of our components so that it would be easy to navigate in the home environment, especially through things like doorways. And our motor choice actually simplified our battery selection by a great deal because it was specifically made to work with a 3-cell LiPo battery. And also, when selecting batteries for drones, it is not suggested to choose anything below a 75C rating because it will simply not be a fast enough discharge rate to achieve flight.
We also decided to implement a state machine for Aria's frame. We chose a state machine because it allows us to create a distinct number of states with which we can transfer between calling each of the functions that make Aria a good personal assistant. On the right, you can see an extremely preliminary drawing that we have for the state machine. On the next slide, we'll see a more current version of the state machine, where Aria is powered on and immediately enters into an idle state, where Aria is listening for a voice call from the user. Aria will then lift off and search around the home using Bumblebee navigation, which is a semi-smart navigation system which allows it to not bump into walls and leave waypoints to follow back home. Once Aria has found a human, it will approach that human and try and determine who that user is. Aria will then greet the user and follow them at a safe distance while listening for another voice call for any of the sub-features of the state machine, either the weather call API, the joke script, or the calendar. At any point, if Aria is unable to find a human, she will return home, as well as if she is less than 10% battery life, or if the user decides to send Aria home, she will navigate back home through the waypoints left behind during Bumblebee navigation and await the user at the home base.
So for our objectives, we wanted to have 2 autonomous navigation modes. The first one we implemented was path planning navigation. For path planning, you set a bunch of waypoints, like Jonathan was saying, for your drone, and they follow this to their final destination. The TikTok runs off a ground station called Q Ground Control. This is what we programmed through, and we programmed 3 flight modes onto our TikTok 4. The first one is takeoff. This arms Aria and takes her off to a designated height of 5 feet. We believe this was the best height because the average height of a human is 5'4" between men and women. Next is altitude. This keeps Aria at 5 feet without oscillation as it's flying to its prepared route. And then finally is return. Aria will fly back to her start position, which in our case is her charging station. This is also triggered if any fail-safes go off, such as low voltage. Our second autonomous navigation was using an RGB depth camera and YOLO. YOLO stands for You Only Look Once and is an image recognition program. This allowed for a more autonomous flight. As you can see in this video, Aria scans the room, and then when she finds a human, she will start to approach and go to a safe distance where then she will follow and await any auditory commands. This was done in a gazebo environment on the Jetson and just needs to be programmed into the state machine.
Now, for user input and feedback, we obviously went with the medium of sound. To accomplish this, we needed Aria to be able to recognize speech. To that end, we implemented Mozilla Deep Speech, which is an open source software developed by adapting a speech AI developed by a company named Baidu operating out of China that was notably powerful in terms of its development for speech recognition. The adaptation was done using a corpus of roughly 7,000 hours of English-speaking voice submissions. And when tested against the LibreSpeech corpus test, which is considered a rather standard test in speech recognition, it achieved greater than 95% accuracy. Additionally, in comparable hardware to the Jetson, especially things like Raspberry Pis and other things that are common to hobbyists, it is known to operate close to or exceeding real time. Now, being that it is such a powerful AI, it is a bit slow on activation. So to get around this, we implemented Porcupine from Pico Voice, which is it is trained to detect a hot word, basically being trained the same way as any other speech AI, but for a specific phrase. In our case, we actually custom trained one to respond to, "Hey, Aria." Now, the other side of being able to recognize speech is being able to hear speech. And as we all know, drones are not silent. Being that we only had available to us a lavalier microphone, which is omnidirectional, due to unidirectional microphones being more expensive, heavier, and a bit on the unwieldy side, I designed a housing using a specific chevron shape that I found in a research paper on how airflow is affected by chevrons in nozzles, to make a housing that would allow sound coming from the forward-facing direction of Aria to be funneled into the microphone itself, and noise from the periphery and back of Aria to be excluded. Additionally, we did add in some noise dampening foam, both in the form of a hard shell that also works as a mounting enclosure for the microphone housing, and as soft foam inserts that work to deflect and dampen some of the sound coming in.
All right, let's keep the ball rolling with some more functionality on the drone. On the facial recognition side, we built a network off of Jetson Inference, which is a platform developed by NVIDIA. It uses a supervised deep neural network that utilizes PyTorch, which is an SDK to help with transfer learning, and TensorRT, which is an open source library for optimization and to speed up that training. We trained our network on about 1,000 images taken of all the 4 group members. And this is a relatively small data set, especially in comparison to a lot of industry neural networks. However, we were able to achieve about 85 to 100% accuracy. And this whole program is integrated onto the Jetson. Keeping things going, in terms of APIs or application programming interfaces, we created 3 main functions, the first one of which is the calendar call API. When Aria is given a specific voice command by the user, it will access the user's Outlook calendar through the Microsoft Graph API, and all authentication and certification is handled by Microsoft Azure. We also have a weather call API, which utilizes a third-party openweatherapi.com website. And we also have a joke script, which currently runs 15 uniquely random jokes. All of these systems are integrated onto Jetson. Now for the part that everybody's been waiting for, administration and project management. On the resource side of things, our budget for this project was about $500, all funded by students. Our total cost was about $550. However, it is worth mentioning that several of the components, such as the Jetson Nano and the Pixar, were purchased outside of the budget because the students wanted to retain full membership of those components after the project is over. Some other resources that we had at our disposal or at our fingertips were the faculty at KSU. Additionally, a fantastic resource is the AUV team. Their Discord link is below. We want to give a specific shout out to PJ and Dante. They're great assets and resources to the team. And I think it's a really good resource and a really good club for anybody looking to get into autonomous vehicles. We also had some open source programs, Python 3, SolidWorks, a bunch of open source AI, and Q ground control. Now, our project was kept track on a Gantt chart. We have 5 major sections for the Gantt chart: the physical design, communication, programming speech recognition, programming navigation/sensing, and developing the autonomous procedures. Our project followed a agile project lifecycle, which means we had regular sprints every week to align teams to the specific goals of the week, as well as frequent feedback and deliverables in terms of the coursework and in terms of internally set benchmarks. The team also kept track of all the hours put towards this project, and we ended up reaching about 350 hours over the course of the semester. Next, John is going to talk about some design objectives.
So over the course of the semester, we were actually able to achieve most of our primary objectives, getting all of our subsystems implemented onto the Jetson or onto the drone frame itself. The only objective that we missed off on was a 10-minute flight time, which could be easily remedied by speccing out a larger battery or having more predefined or specialized hardware for the drone.
Now, in the future, one of the main things we'd like to do would be seeing Aria made into a more marketable product. This means adding additional functionalities, such as recognizing gesture commands or locating objects around the house so you've lost a wallet or a set of keys and simply just want to, say, have someone else look for it. Aria would do this and then alert the user if the object is found. This would also be a great way to utilize more of our facial recognition work. Speaking more to specialized hardware, the Jetson Nano is a powerful device, but being that it's a development kit, it has a lot of resource overhead that we feel can be better utilized in a more specialized configuration and would also help with our power consumption reaching our desired flight time. Additionally, obviously, we would like to give Aria more of a sleek design to keep the wires with many given users and also just to have a nicer piece around the house.
Some other future work that we want to implement is to flesh out the backend. So there are a couple shortcomings in the software that we wrote. Primarily, the calendar call API requires the user to manually authenticate and refresh the credentials to access the user's calendar. For a more micro product, we'd obviously want to automate that so the user doesn't have to worry about that. We'd also like to implement a unsupervised deep learning neural network so that the user doesn't have to sit down and take a bunch of photos of themselves in order for the drone to recognize it.
So we feel like it would be kind of shortchanging ourselves not to recap what we were able to accomplish this semester. We achieved 95% completion of this project, the 5% being complete integration onto the drone frame and the 10-minute flight time not being reached. A lot of these complications came up with unfamiliarity with drones and the subsystems that we decided to implement on top of the drone frame itself. We got to remember this project is extremely ambitious. We built a drone frame up from scratch, and Darbey was the lead on our navigation, just creating that out of nothing using Gazebo and a whole bunch of other resources. And then we decided to add on different APIs, different AIs, things that we were completely unaware of, and decided, yeah, let's do it. We also are super proud of the solution for a unidirectional microphone coming from an omnidirectional microphone, and how organized and focused our group was able to remain throughout this extremely stressful semester.
So finally, here's some of our literature review, and we're excited. We got a lot from GitHub repositories, some research papers, and YouTube has been an amazing resource as well.
That concludes our presentation. How was that, Zane?
Well, I just want to start by personally thanking you, Peter, for allowing me to be a part of attending that presentation. It was absolutely incredible, and I'm blown away with the work you guys have done. This is the stuff that hooked me in the beginning, and I hope everyone watching this is getting some excitement for what we do here and what we're capable of. Let's queue up some questions. Let's hammer them pretty hard. They did an amazing job, so let's not let them off the hook. Let's ask them some super hard questions and see how they do.
For setting up a new user, currently we would have the user training the face recognition AI by themselves, but that is something that we would like to fix in our future work, allowing the neural network to do unsupervised training of the user.
Currently, we are just using a simulated depth camera. That was something that was difficult to get in reality because they were kind of expensive, but we would want one that was open to use.
And to answer your question, Alex, the software, like I said, is not trained on a lot of data sets. In order to differentiate between a mask and a reasoning face, it can't do that right now. We actually benchmark it with photos of the group members. What we did do to, I guess, refine it a little bit is that just because the project is trained on 4 faces, we set the threshold or the confidence value to a little bit higher. So if somebody else walked into the room, the drone wouldn't say, oh yes, this looks like Darbey. Let me identify her. So to answer your question, really, it would just have to be training on more data. To answer your question, Zane, absolutely.
Definitely a wise choice.
Best solution right now for the audio.
All right, let's get on with a couple of last questions here.
Alex, to answer your question, the AI does use a deep learning neural network. We did have to feed it a bunch of photos of our faces, capture them on bounding boxes, train to recognize who is what. Jacob Bell, no, does not. It's awfully complex and difficult to play.
And Charlie, we believe that the benefit of having this on a drone platform allows it to be a novelty, of course, but also allows it to follow the user around the house without having to make multiple units available throughout the house.
And as far as the privacy implications, that would definitely be something for future marketability. It would have to have something where it's updated, and so you couldn't get into those.
And some of the more tangible benefits of making it a mobile platform as opposed to something stationary are covered more in our future work than our current application.
Thank you, Zane, and thank you, Marshall, for the opportunity to do this project and have a great senior design semester. You're very grateful for the tutelage that y'all gave and all the advice, and wish you guys the best in future semesters.
We would also be remiss if we forgot to mention thanks for all of our family members and friends who were able to join us today for this presentation. We appreciate y'all's support.
All right, nice job. Super proud of you guys. Awesome, awesome job. Give them some good applause in chat while we queue up the next team. All right, nice job. Super proud of you guys. Awesome, awesome job. Give them some good applause in chat while we queue up the next team. I'm impressed. That was pretty awesome.